Alright, so we left off in that last little video about looking at odds against something. So I'm going to skip the your turn problem at the very beginning here. I'm going to let you do that after we finish the last example here. And this one, these used to be called Mendel's squares, but now they are more likely to be called something called a Punnett square. And the Punnett square is the same thing as Mendel's square. It's based upon the idea from genetics of finding probabilities. And so when we do one of these Mendel's squares, it's kind of like what you do when you do a factoring box in intermediate algebra or an algebra class where you're trying to do some factoring and you take a look at the factors of the first and the last items, the constant and the squared term in factoring a polynomial. And you look at the crossovers and then you look at the factor boxes to try to find out those. Anyway, that's kind of where the similarity ends, but we're going to do the same thing here. So we're looking at a genotype based upon the alleles of from a gene. So if we have a blue-eyed or a brown-eyed mother and a brown-eyed father, so we'll put mom up here and we'll put dad down here. And if mom and dad are both brown-eyed, that's their phenotype. But mom and dad could carry a brown-blue allele. And the brown, being the dominant of the two, will lead to having the phenotype of brown eyes rather than blue. So if mom and dad are going to have kids, then the different genetic combinations here are shown based upon this Mendel's square or this Punnett square. And so what we have is a brown-blue combination here, so this overlaps with this, and here we have a blue-blue combination, and then here we have a brown-brown combination. And then in the last box here we have a blue-brown combination. Now this is the list of simple events that occurs, right? But what we're really interested in is the brown and the blue. I don't have a brown for my thing, so I'm going to use an orange. And so the phenotype here, this person would be brown-eyed, and this person would be brown-eyed, or this would result in an offspring with brown eyes, and this one here would also represent a brown-eyed offspring. And so the very last one, where those alleles that were both blue got together, that's where we could see a blue-eyed child come from. And so what we see is based upon the sample space, right, the brown, blue, 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 brown, brown, blue, brown, that we could get an event of brown or blue occurring, right? And there's 3 choices where brown occur and 1 choice out of blue, out of the 4 possible simple events. And so what we have is the probability of getting a blue-eyed child looking like 1 in 4, whereas the probability of getting a not blue-eyed child, in other words that brown-eyed child, right, let me put this in orange, this one equals 3/4. And so that is going to represent our 2 possible mutually exclusive events. You're either blue-eyed or you're brown-eyed. We're not looking at codominant traits here. We're just looking at these as being strictly dominant and recessive. And so we have these probabilities. So our problem says, what are the odds against having a blue-eyed child if both parents have brown eyes based upon a brown-blue genetic combination? So what we see here is the odds against a blue-eyed child. This would look like the probability of not blue divided by the probability of a blue. And so our probability of a not blue, we could do this the long way, but this would be crazy. We'll do it anyway. But the probability of a not blue is 3/4, and then the probability of the blue is 1/4. Well, the problem with doing it this way is that everybody goes, oh gosh, that's fractions, oh, scary, scary fractions. Well, they're not really scary if you just calm down and you take a look at it and you go, oh, well, this means 3/4 divided by 1/4, right? Because that's what that fraction bar means. And everybody should know how to divide fractions. This is 3/4 multiplied by the reciprocal, that's 4/1. And then we see, oh, well, those two 4's are the same, so they cancel, and this looks like 3/1. And remember that one of the ways that we can create that is by saying, how many ways can blue not happen? 3. How many ways can blue happen? 1. And the odds against blue happening is 3/1, therefore. And that's exactly what we got by going at it by the probabilities. But see how much easier it is when we think of that rule where we say, oh, if it's how many ways can it not happen and how many ways can it happen, and you see if you add this up, this is the total number of outcomes, right? There are 4 simple events there. So that's another way of looking at those 3 factoids about odds problems. So I'm going to go ahead and let you guys do this problem, the your turn problem, on your own. So why don't you go ahead and pause your why don't you go ahead and pause your computer, and why don't you go ahead and try to figure that out. So I'm going to leave you with this here on your screen. So here's the problem down here, and those were all of our little sets of information, and you can see how you do on this, and we'll come back and do it in just a minute here. So, what are the odds against choosing a man in a room where there are 12 males and 18 females? So, we want odds against a male. So, I need the probability of a male and the probability of a not male, right? Those are the things that I am interested in. And I really don't even have to find probabilities here if I don't want to, but the number of males in the room are 12, and the number of not males, that would be, of course, females, and maybe it's a good idea to write that down so that you see, yeah, that's what we're talking about. Those would be 18, aren't they? And so if I wanted the not male, and I'm just going to abbreviate that with an M, and the probability of a male here, what I have really going on here is 18 to 12, don't I? And that, of course, just simplifying because this and this are both divisible by 6. And you know you don't ever leave fractions as unreduced, so this looks like 3 to 2. And that would be our odds ratio right there. And you see that this is going to give us the same thing as 18 over 18 plus 12, which is 30. So 18 out of 30 gives you 3 out of 5, and 12 out of 30, which gives you 2 out of 5. So we can see the same odds there, and that would be the very easy way of doing it. But we wanted to start by defining A complement, the probability of A and the probability of A complement. So we really should have found this, and then from there said, okay, well, what's the probability of, let's see, let's go with the black here. The black. The probability of a male, and that would be 12 out of, and this would be 12 plus 18, that's where I was getting the 30, and this 12 out of 30 is of course going to reduce down into the 2/5, right? Because divided by 6, 2 and 5. And then the probability of not being a male, that would be giving us the 18 out of the same thing, the 30 total number, and divide by 6 is 3, and divide by 6 is 5.